the super-ionic conductors, fast ionic conductors. Last time, actually, we have discussed about the simple hopping model, right? And today we are going to discuss about the parameters in simple hopping model. Well, the simple hopping model is nothing but the random walk formulation for defect transport. By isolated jumps. The reason why we want to study on this simple hopping model is that in a super-ionic conductors, there is something else than the simple hopping for the diffusion. And we put the parameters for the simple hopping model, and then under this incredible, what should I say? It's not the practical assumptions we have to make to get the simple hopping models, the numbers for the conductivity. And then in reality, we have a very close numbers that we can get from the simple hopping model under the very severe assumptions. So we want to get a conclusion that in the super-ionic conductors, there is something else than the simple hopping of the defects and things like that, okay? So, in diffusion coefficient can be written as the frequencies and geometric vectors and the hopping distance thing, okay? Alpha as a geometric vector. So for closed packed cubic lattice, that is going to be 1/6, and one dimension analysis, it should be 1/2, things like this, okay? And D is single jump distance, and nu is average jump frequencies, and the nu is beta nu naught exponential minus theta g over RT, and beta is fraction of the species that is free to move. And nu naught is attempt frequency. Exponential minus theta g over RT, possibility. Of success. where the G is free energy of migration. D now is upper D square beta nu not exponential delta S over R exponential minus delta H RT. And beta is exponential minus delta GF of RT and the GF in terms of defect pair. So we plot the D versus 1 over T, and the slope is going to be minus delta H plus delta HF of R. And here delta HF enthalpy of defect pair formation. Now the important thing is this is negligible in first ionic conductor. So first ionic conductor case, beta is large and not a function of temperature. So in plot of 1 over T, and then slope is minus delta H over R, and this is enthalpy for motion, not the formation. And Nernst sigma is dc square So we can conclude that the fast ionic conductors delta S and nu naught is very small for small value of sigma naught. And also the activation energy very small. Means high probability for success of jumps. Okay, so you can have important conclusion that the FIC should be extremely sensitive to crystallographic considerations. And not the presence of unusually large concentration of mobile species. Here the crystallographic consideration means the geometry of the static part of the crystal structure. That is a crystal structure, okay, and potential energy profiles. Along which the mobile ions move. Okay, so in the handout that I gave you, there's a detailed description of 4 kinds of crystal structure which shows the fast ionic conduction. And one is in a cubic structure, And there's examples for this, like silver iodide and thing, and hexagonal structure. It has a very open space, and unidirectional tunnel structure. Okay, and layer structures, like a beta alumina. Okay. So you can find a detailed description of these structures in the handouts. And the reason why we have to discuss about this crystallographic structures for the fast ionic conductor is that the fast ionic conductor, the characteristic of a fast ionic conductor cannot, fast ionic conduction nature cannot be explained by the presence of large number of mobile species. Because in a simple hopping model, every jump is successful, and we have enough, every ions is mobile. We assume that, and then we have a certain number, but which is not realistic at all, right? But in a superionic conductor, we have a very close numbers to that, or even higher numbers than the theoretical simple hopping model. Now, how can you explain that? And the only way to explain that is we have to think about the open structures in fast ionic conductors. If we have abnormally low potential energies in a cubic structure, or if you have abnormally open structures for the mobile species in hexagonal and the tunnel and the layer structures, like a beta alumina and potassium hexatungstates and so forth. So you guys have to look into the details of this, which is described in the last section of the handouts to understand the fast ionic conductors. Let me finish this lecture by saying that the energy is very important. And it becomes more and more important because everything becomes mobile, like a robot is a good example that that the sophisticated devices has to be mobile. And once your device is mobile, then the energy is the most important thing. Okay? But as far as the battery system is concerned, we have a long histories. But basically, the charging reactions and discharging reactions and chemical reactions are driven by electrical potentials. All those things are just conventional. We really didn't have any breakthrough. Like conductors, we have a superionic conductors where the resistance is really zero. That is a big breakthrough, even though it is not industrialized yet. But in battery system, in energy systems, we haven't experienced that big breakthrough. We are using same theories. We have lithium batteries, nickel cadmium batteries, and lead batteries. All those batteries are available in the market. We don't have any big breakthrough, new battery system yet. And with a discussion in detail about the electrochemistry, what's happening inside the batteries, probably we can have a new insight to find new materials which give us a high efficiencies, energy efficiencies and so forth. Okay? And we need that. For example, durons. Everybody know about the durons. In durons, the battery is the most important. That is the bottleneck to develop heavy-duty durons. And the electric car. And in China, last time I visited China a month ago, and at night, in China, there is a lot of scooters, small autobike, scooters, and they changed every scooter's it's electricity. That's driven by electricity, electric scooter. And there's no sound at all. It moves without any sound. So at night, electric scooter was passing by, and I didn't notice that. There's no sound at all, and no pollution. And the only problem now is it's heavy. They have to charge it every time, like every 3-4 hours and things like that. That's the problem. But we can solve that with finding new materials, like a fast ionic conductor for the electrolyte and fast ionic mixed conductors for the cathode. Then you can have a high efficiency batteries, and then we can solve these problems. For future robot, the function is not important. How long my robot can run, that is important. No matter how powerful your robot is, if you can use your robot just for 30 minutes, then what's the use, right? What's the use? So I hope you guys realize this trends in technologies, and more students should involved, I think, in electrochemistry to finding new energies. Okay, let me give you the hint about the finals. The finals basically is not supposed to be difficult, like undergraduate or the high school stuff. Okay, you are masters and PhD students, so I believe in you. So I don't want to make difficult questions, but I want to have a sincere answers to the questions. So even if you come to the questions which is not familiar or which you do not know, you have to make a big search with the internet, okay? You don't have to know everything. Everything is on the internet. So only thing you guys have to know is how to use that information. Maybe that is more important, okay? So in that respect, your final exam, it will have 1 or 2 questions only, and then you have to do a lot of intense search on the internet. So bring your smartphone or the personal computers, and just take 2 hours, but if you can finish it within an hour, no, what the hell, just get the answer. Everything has to be written in English, except your name. Of course, the foreigners, they have to write down their name by English, but Korean students, they write down their names in Korean, but all answers should be said and written in English. Any questions? Okay.